when you talk about principle of moments and when we're trying to balance everything out, rotational equilibrium is reached when the sum of clockwise moments and counterclockwise moments is equal to zero. So this is just a way to word this very simple equation, which is the sum of moments is equal to zero. Okay, so when clockwise and counterclockwise are equal, then that means that we have rotational equilibrium. And when you're going to design buildings or structures, okay, let's say you want to design this bridge and it's supported only on this side, okay? Now, you're going to put a person here. He's going to therefore have a bit of a moment. You want everything to be perfectly balanced. You need to be able to calculate, okay, how much support must I put here such that it will be balanced? Because if it's not balanced, then you're just going to have this guy go down and it's going to be like a diving board. But I don't think you want that in a bridge, don't you? Okay, so we want to solve for rotational equilibrium in moment problems. Now, here are some example problems. Let's start with a simple one. Okay, so let's say we have a 200 Newton child that is seated at an unknown distance from the pivot point, and he or she, I can't really tell, is balanced out by this 400 Newton child seated 1.5 meters away from the pivot point. Now, from inspection, they are not the same mass, they are not the same weight. However, there is a way to still achieve rotational equilibrium, and that is if their moments are equal. Okay, so this girl, I'll just call this the girl. Okay, this girl exerts a counterclockwise moment. This one, as you could see, would exert a clockwise moment. And by the equation, we know that the sum of all moments must equal zero. That means that the counterclockwise moments plus the clockwise moments must add up to zero, or they are essentially equal. And if we look at it, okay, which is the counterclockwise moment? Well, we have this girl over here who has a 200 Newton force or weight, and we actually don't know the distance, so let's just label that B. Now, how about the clockwise moment? Well, we have this boy over here who is seated 1.5 meters and 400 newtons. Okay, seated 1.5 meters away from the support and 400 newtons of weight. And we know that to be negative, okay, because it's clockwise. So we have 1.5 meters times 400 newtons, okay? And we know all of that to be equal to zero. Now, I think you can rearrange this simply in order to get D, and that will be 400 times 1.5, and you can put that to the other side, divided by 200 newtons should get you the distance required. Okay, now let's go and grab my calculator real quick. I'll just keep these annotations as said. Okay, so that would be 400 times 1.5 divided by 200 gives me a moment of 3, or rather a distance of 3. So when we go back to this slide, okay, if this girl is seated 3 meters away from the center of support, then they should balance out, and that makes a bit of sense. Okay, if you want a heavier object, if you have a heavier object, you want them to be closer to the center of support. Okay, and that will mean that closer to the support means less moment. So 3 meters is the final answer for this problem.